right, time for another DraftPhysics.com, DebatePhysics.com also. Both websites have some videos that are on this channel, DraftScience on YouTube, indexed to some extent, pointed to certain subjects. So the Debate Physics website is mostly about the subject of 1/2 mv squared, the kinetic energy formula, the idea that momentum isn't energy, that something else is, that you can square velocity, all that kind of stuff. And how there's zero evidence. It's just a flat earth pile of nonsense. They claim they're doing science when they don't care about evidence. And you can't do science if you don't care about evidence. So Professor Dave is a fool and a dupe and a stooge. And he wouldn't be any of those things if he wasn't a jerk and an asshole and a coward. If he'd actually listen to the arguments, pay attention, go look at the simulation of charge, and have to concede, yes, it works. The alternative theories are viable and real, and they should be fairly considered. And especially in the context of you not having any evidence, real evidence, credible evidence, proving what you claim to be a fact. But they won't do that because they're rotten, stinking, crappy examples of human being. They haven't acquired any integrity or, character. And so they can't do good science because they're dishonest, conniving, scheming, self-interested pieces of shit. Yeah, okay. So that's the dilemma. All right, so this subject is thermodynamics, the vibrating number. Wonder how that's going to look. Yeah, anyway. And the second law, which is the silliest of the thermodynamic concepts. I mean, obviously, the idea that there's a conservation of motion in the universe isn't all that challenging, or there's not much dispute, I guess I would argue. Not too many physicists are going to disagree that you can't make it and you can't destroy it. Those are the rules by which the universe functions. But what they miss is the most obvious, biggest part of the cycle of heat in the universe. So they talk about thermodynamics and they miss the event that is the most dramatic thermodynamic event in the universe, which is gravity. Okay, so the bent space, which is just, you could just draw it, okay, and you can draw the inverse square line law in a sense if you disproportionately make lines coming out of the center. I should make them come out of the center of the earth. That would be better. In terms of how much these lines separate with distance. And so the inverse square would be a certain separation. And you can sort of understand that the further apart these lines are, the less dense the force. The closer they are together, the more concentrated the amount of stuff. Okay. And so all big masses in the universe will experience an increase in temperature. So they have a constant amount of pressure being applied to their surface. Every new piece of matter that sticks to them applies a constant pressure towards the center. And the center can't cancel the energy. You can't just bang it into each other and it disappears. No, it constantly is a war going on between the pressure from one direction and the pressure from the other direction. And it's sort of at a pressure equilibrium. But the fact is that it does dissipate out of the earth and create a real equilibrium with the universe over a completion of time. And the trick is it's not a completion of time. So the simple argument is when you're standing on the earth, what's really happening is the universe, the universe, okay, is hitting you with heat from all the other little stuff in the universe. All the planets, all the suns, all the galaxies, everything is bombarding you with energy, okay, in the form of some kind of photon, visible, invisible, doesn't matter, some kind of background radiation. And the simple truth is the energy that would equalize that. So if you were in space and there was nothing below you, no matter, then the two forces would hit you at the same time. And the simple argument is the force coming from below can't hit you at the same time because it has to go through a bunch of matter and push it and create the pressure in the center of the earth. And so that differential is what you're being pushed into the earth with. And that's all creation of energy. So when an asteroid hits the earth, say gravity gives it velocity towards the earth. And yeah, so we had a velocity going some other direction. We'll just ignore that and just count the amount of momentum created by the Earth's gravity. And it's a real momentum, and it hits the Earth and it applies a pressure. And now its mass is on the Earth, and that's going to apply a pressure. So it's constantly heating the Earth. And the heat is real. So we know that the heat has to dissipate. I can't put heat into something and somehow it just goes away. We know it turns into radiant energy, photons, infrared photons, microwave photons, radio photons, lots of kinds of photons. So we know that's what the heat's going to do. So we know it's real energy in the universe now. So why are we talking about bent space? I mean, obviously the heat cycle, the biggest heat cycle in the universe is the fact that heat radiates in all directions from a material object in space, and the heat also goes in to every material object in space. And that's the real cycle. And we know that the heat gets concentrated in the small space of the center of that object. And so that's your anti-entropy mechanism. So the biggest anti-entropy mechanism is a force that looks like entropy when it's coming out, but it's anti-entropy going in. And so that's the real heat cycle of the universe. And you could call it perpetual motion. So we can say that, okay, perpetual motion is impossible. But we know the universe is in perpetual motion. So we know it's not impossible because the universe is doing it. But it's only impossible when you have a bunch of friction and air and all kinds of other shit to get in the way. Then it's impossible. But clearly the universe has created a forever cycle of compressions and expansions and, condensing energy and then dispersing energy. And so there is no entropy problem. There's no point where energy becomes meaningless and useless. So any energy dissipated by any object in space, you can be pretty much guaranteed that that energy is going to find a home, okay, on the surface of some other material body and create the very compression that it was a byproduct of. And so they think they know something about the universe's thermodynamics when they don't have any of this stuff right. Alright, so let's go to the videotape. So the second law of thermodynamics, which is their argument that somehow energy dissipates into some sort of uselessness, which it obviously doesn't.
The first law of thermodynamics told us about the relationship between internal energy, heat, and work.
So
the second law will introduce one of the most
really didn't do any of that internal nonsense.
Confusing concepts in physics, entropy.
So again, there's no entropy in the fact that the energy doesn't get disordered. The energy isn't in, it doesn't make any difference whether, even if the energy could be in 10-pound clumps and 5-pound clumps and 1-pound clumps, it wouldn't matter because it's all momentum. So it all comes down to just mass moving. The force is a very small, discrete, tiny mass moving a velocity, the speed of light. So very tiny m, very big v, and every other material object that collects that force ends up having a mass and a velocity. And that's all that really is. And it doesn't matter about order or disorder, but it certainly matters about the fact that you can have heat with a very decided direction, like electrons flowing through a wire, or a laser beam, or you can have heat that's dispersed and going in all kinds of directions. And obviously one is a lot easier to collect than the other.
Let's go through this law and examine how the concept of entropy was derived as a result.
So it really wasn't derived as a concept. It was just stated and observed. The simple truth was is what they were getting to was this idea that heat is the same as work. And it's just some percentage of the work is lost as heat. And the work itself will convert into heat. So when you're done doing the work, where does the energy go? Well, it dissipates as heat. But that's the whole point, is you're only using momentum. You use it, and then it's not that you lose it, but yes, it does go into a form that's not immediately useful. But in a sense, you could always just keep using something's momentum perpetually over and over and over again if you just create systems to collect it. So if you collect, say if you hit a bowling ball into the pins, well, if you create a device that has a bunch of springs that collects all the energy from the springs, you can understand that you could charge batteries, or you could do something with that energy and then reuse it again, and then use it again, and use it again. It's just that that's not efficient, okay, for our purposes. It's too hard. It's too much work, energy, to create the system to collect it than what we can collect. And so, therefore, we don't bother.
The second law came about through the work of a fellow named Sadi Carnot and his study of heat engines.
And he died tragically of cholera, being a nice guy gets you in big trouble sometimes. Helping people, got him killed.
A heat engine is one that absorbs heat and uses it to do work, like the steam locomotives of the 19th century.
So they're not really, this idea of using heat, they're using, again, you're just using motion, pressure, momentum. Heat creates pressure. The pressure is what you're collecting. So come on, it's not really a heat engine. And the chemistry can be, lots of different kinds of chemistry can create expansion, so they don't all have to be so directly related to something called heat.
Which absorbed the heat from a coal furnace to generate...
You could use the expansion of water, okay, the fact that water expands as it freezes. You could use the opposite of a heat conversion in the sense that you pull the heat out of the water, create an expansion, and you could use that pressure as to do work. So it's just not as they're describing it. Motion is all you're really after, and you can get motion through other mechanisms besides the one direction. Just like we're collecting the rain as it falls on the earth, we're really collecting the energy that gravity is creating. And then we could collect the energy of a volcano exploding. One of them's the energy spreading, one of them's the energy consolidating. And we can collect the flow in either way, either direction. Either the direction of it being consolidated or the direction of it being spread.
Steam, which would then move pistons connected to the train's wheels. Excess heat from the hot reservoir that is not actively used to produce work will move to a cold reservoir, which has a lower temperature than the hot reservoir.
This is kind of a weird way of describing how the work is actually accomplished. And the real point is that once you have the expansion, you have to recontract the system to expand it again. So it's something like alternating current versus direct current. And while one of them works as an induction process and one doesn't. So the only thing you're doing here is really getting rid of the condition you created, which is equilibrium. And you can't move the heat into equilibrium. You can't move the heat into a hot place. You have to move the heat into a cold place to do work. So the price you pay to get work out of the cylinder is you have to dispose of a bunch of heat.
Carnot understood that the maximum work, or W net, that can be done by one cycle of such an engine is equal to the heat input, or QH, minus the heat output, or QC.
Yeah, minus the amount of heat it takes you got to pull out of your cylinder. Once it's expanded, you have to get rid of it. So in a combustion engine, you get rid of the hot gas and you cool the engine block, which you probably don't have to do except for the limitations of, metals. probably be like diesel. You keep it hot because the heat basically ensures the firing of the gas in the next cycle. But the truth is, you still have to remove the waste products. So there's always going to be waste products, and you're always going to have to pay the price of removing them.
Since any heat loss
Or a waste condition, you could even call it that. The piston has expanded, and you have to recontract it, frankly.
will not be able to be converted into work due to the first law of thermodynamics. If there was truly zero heat loss, we could say that all of the heat is transferred to work and the engine operates at 100% efficiency.
So there's no point in really talking about it, just because obviously you're taking advantage of the pressure created by the heat. All right, so there's a specific thing you're taking advantage of. And again, it's like AC current. You're just, the liability is you can't just, you have to let the system equalize to do it again. And then you have to let the system equalize to do it again. And so to make it more expedient, we're equalizing it by applying or wasting some energy.
Unfortunately, this is not physically possible for a number of reasons. First, the only way to achieve 100% efficiency would be if every process in the engine were completely reversible.
So this idea of even playing with reversibility. So for heat, you can imagine the reversibility isn't that complicated. It's just the difference between imagining the sun emitting photons at the inverse square law and then imagining gravity absorbing photons at the inverse square law. So it's pretty easy to imagine the system, and that's all you really need to understand, is it in bold terms. But saying you could reverse the system requires you can't just play it backwards, because all the timing is wrong, because there's so much friction involved, and friction makes things go slower with time. And obviously if you reverse that, then things will go faster with friction, and that wouldn't make any sense. So there's lots of ways that this idea of trying to reverse it fails.
Meaning both the system and surroundings could return to their original states. This is known as Carnot's principle.
So there's no real, it's like imagining an egg unhatching. Come on, yeah. Well, yeah, it's theoretically you could figure out how to make it artificially, but you can't sit there and unhatch an egg.
But any real engine involves moving parts that produce friction and sound, so some energy must always be lost to the surroundings. This conclusion does not immediately follow from the first law of thermodynamics.
So again, where's the law in any of this? Where is the concept? So there's no law here. He's just talking about the efficiencies and inefficiencies of any kind of system we create to collect motion. And what does that have to do with any kind of law that somehow heat only moves in one direction? When, again, the Earth is a perfect example of the consolidation of heat, not the spreading of heat. So again, it's just so obvious that, the Earth's core is 4,000 degrees centigrade, something like that. We don't feel it, but it's there, it's happening. Nothing didn't make it. You can't just sit there and deny the existence of that furnace. And it has to be constantly fueled. It's not like, it got to be 4,000 degrees a million years ago and it just stayed there. It's not happening. It's constantly being fueled by gravity.
So it was formulated into the second law, which states that no cyclic process can convert some quantity of heat entirely into work. So
now he's saying that's what the second law of thermodynamics says. So it's like, what does that even mean? Okay, cyclic process. So we know the universe is a cyclic process. So I'm just saying, it's happening all the time in the universe.
Some of this heat will always be lost to the surroundings.
So there's no way to lose it, because the surroundings are your system. So as long as your system collects it, then you haven't lost it. So it's just a matter of making your system closed. And yeah, that's expensive. It's expensive to collect the bowling pin energy. We could do it, but it would be expensive.
This is a variation of another way of expressing the second law, which can also state that heat spontaneously flows.
So the word spontaneous is just a terrible, awful, almost evil thing to say. So there's nothing spontaneous about it. The heat is actually moving. The cold stuff is moving less. So obviously the heat moves from the place where there's more motion to the place where there's less motion. I mean, duh. And so you just use the extreme of something not moving and something moving, and you know the only thing that can happen is the moving thing is going to make the not moving thing move. There's no alternative. You can't have the non-moving thing cause the moving thing to not move, and now they both don't move. That's not an option. So you know the heat has to be shared. The motion has to be shared.
From regions of high temperature to regions of low temperature, and not the other way around. These expressions can be...
Non-moving things don't have energy. They can't give anything energy. That's kind of a silly way. Why would you even write that law? It's so silly. So it's so simple and so obvious.
Considered two sides of the same coin, since heat, therefore, can't flow spontaneously from the cold...
So again, using the word spontaneous, nothing would be spontaneous. The heat takes time to move. We all know how slow it is in some cases. So what are we talking about anything spontaneous for?
Reservoir.
We know there's actual causes and effects. Nothing just decides to move.
To the hot reservoir of a heat engine, further supporting the idea that heat is always lost to the environment as the engine runs.
So again, it's there's no rule that you lose anything, and all that's really happening is, generally speaking, it's easier to put a boat in a river than it is to put a boat in an eddy or some other, if you want to get somewhere, you have to put your boat in a stream. You can't just put your boat in a bunch of agitated water. Agitated water won't make your boat go anywhere. That's the simple rule. But there's nothing saying the agitation or the motion in both cases isn't real. Shaking something, same energy as throwing something.
But this is not just a limitation of our technology.
Yes, it is. It's just a limitation of our application of technology. If we really want to do it, we can perpetuate the energy. We can keep collecting it.
Purely hypothetical, perfect heat engine, called a Carnot engine, can never operate at 100% efficiency.
Yeah, because it can't escape the same liabilities. It's got to move something, and it's not going to move it in a perfect space and all that kind of stuff. So a Carnot engine in space might be able to achieve a much higher efficiency. But the fact is, as soon as you start moving something inside a piston, you got to have rubbing surfaces. You're doomed to lose a lot of energy. So yeah, you can't make it perpetual. But in space, maybe you can.
This is a mathematical limitation of heat flow. Whichever way we choose to look at the...
So there's no mathematical limitation. You can collect infrared radiation, or you can collect a rhinoceros plow into the side of your car. You can collect motion, any motion, always. It's all collectible. So it's just wrong to say there's some force we can't collect, or there's some matter moving that we can't collect its energy. Of course we can. It's just sometimes really hard to do it.
Second law, it will inevitably result in the discussion of a peculiar concept called entropy.
So there's no concept here. So there's entropy in the sense that if I have a million different colored beads and I throw them, there's millions and millions and millions of different ways they could arrange. And there's all kinds of laws of probability dictating what kind of relationships between them there can possibly be. Hitting a bunch of pool balls, a rack of pool balls, and there's all kinds of different ways they can leave the rack. That's a different subject. the idea that you can create things that are chaotic are complex, but there's nothing innately complex about the flow of motion. Motion flows, okay, it moves, and it moves by just following essentially force. The force pushes the matter, so the force has to be acquired by matter, and you can basically follow that collection process.
Entropy is a term that represents the inevitable partial loss of a heat engine's ability to do work. It is a state function.
No, it's really just nonsense. Its ability to do work, its efficiency, is the real limitations are our terrible environment. In the sense the environment has not only atmosphere, but it also has gravity, making it very difficult to create any engine that isn't going to find that circumstance detrimental to its function.
Measured in joules per Kelvin, and it will be represented by the letter S. The change in entropy is given by...
This is all just made up. You shouldn't even write this as mathematical formulas because it's so vague and foggy and imprecise.
By heat over the Kelvin temperature for a reversible process. And a mathematical ramification of this expression is that the change in entropy is 0 for a Carnot engine. This can be extended.
I don't know why he's saying that when he just conceded you can't make the Carnot engine that efficient, but whatever, who cares?
To say that the change in entropy of the universe will be 0 for any reversible process, where the universe is understood to mean the system plus the surroundings.
So again, he's talking about the universe, and there's talking about some idea that this second law implies that the universe is going to run out of energy or it's getting colder. And the fact is it's constantly fueling the batteries. That's what gravity does.
However, no process is truly reversible. So we should rather say that the change in entropy of the universe for any spontaneous process will be greater than 0, or that for any spontaneous process, the entropy...
So there's no spontaneous process. So why would he even use this word? I mean, it's just such a... you don't have to be much of a physicist to realize you don't really want to say words like random and spontaneous and instantaneous or any of that kind of stuff, because they're all mushy concepts that don't really mean anything. Nothing happens without a cause. Spontaneous doesn't mean anything. It doesn't mean anything in physics.
Of the universe is always increasing, which is another common articulation of the second law.
So that's just not true. So as much energy is being pushed into empty space as empty space is pushing into the formation of gravity collecting mass. So masses are growing just as fast as the energy is collecting in space. There's just as many objects emitting photons as there are objects collecting photons. And the collection process is consolidating the pressure, and the emitting process is spreading the pressure.
The implications of this law are so astounding that they have philosophical impact.
So this is just hilarious. There's no philosophical, in a billion years the earth will, or in a billion years. Yeah, that has philosophical implications. What's going to happen in a billion years? Oh, please. To what lunatic?
If we take entropy to mean disorder, it shows that the universe tends to move towards maximum disorder.
So there's absolutely no evidence that all those objects are constructed by the universe. The universe is actively constructing those objects, and yet they're going to pretend that somehow those objects are all going to run out of fuel, even though gravity's constantly fueling them.
And while order can spontaneously form on the local level, like when water...
So again, it doesn't happen spontaneously. Why is he using... He has that word in big red letters. Why is he using a word like that? There's no such thing. It has to be seeded by something. There has to be a spark that creates the flame. There's no spontaneous.
Freezes to form ice, or in the case of any living organism, this will always be accompanied by a dispersal of energy that increases the disorder of the universe as a whole.
So more nonsense, that somehow you create this more disorder by, even when you order something, you're creating more disorder, which is just absolute nonsense. So there's no disorder. If we took all the stuff, the complex chemistry out of the universe, and all you had was the suns burning and the planets orbiting and blah, 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 it would all be quite obvious that, no, consolidating the energy in the matter doesn't hurt the energy, doesn't degrade the energy, doesn't harm it in any way, and it will eventually all be radiated back out again. It's a completely self-perpetuating mechanism of energy, and because of charge, that's the real catch. That's why the energy is funneled to the center of the earth in a way. It's because of charge that enables you to consolidate and then eventually, some later date, unconsolidate.
Entropy can be rationalized if we examine the concept of microstates, introduced by Ludwig Boltzmann.
So this was a big mistake, Boltzmann. He had a lot of wacky, stupid ideas, frankly.
A microstate is simply a specific configuration of all the...
I thought he committed suicide. I didn't realize he had that big giant beard. Anyway.
...particles and energies in a system. The dispersal of matter and energy, which is always accompanied by an increase in entropy.
So again, the dispersal is entropic, but the exact opposite is happening with gravity. So you can just see from this example, they're pretending that all the energy events in the universe are going out. And they're just pretending that somehow the one going in isn't creating energy, because they have this silly bent space thing. And bent space can't be a process that has energy in it, all right? Because it's supposed to be a bent nothing. It's not supposed to be a force. But the truth is, it's just the opposite. It's just that in reverse.
Will tend to be spontaneous.
Things move towards spontaneous again. There's nothing spontaneous. There's got to be some precondition, and then there's got to be some event that triggers, blah, blah, blah. Guns don't just fire spontaneously.
More disorder because of this equation, where S equals K, the Boltzmann constant, times the natural log of W, where
what the hell could this possibly mean to something? The natural log of W, whatever the hell that could be. So you just imagine how this is just some vague, mushy number. This isn't, this isn't really science.
W is the number of microstates possible for a system.
So again, the microstate, so this is the probability part. So Boltzmann's talking about probability. He's talking about mixing things, mixing black, white, and green balls or something, and saying how what's the most chaotic state they can be in versus the least chaotic state they can be in, what probabilities and all that stuff. That is not heat. Heat does not mix in some way. Okay, it either exists, is something's moving, or something's not. There's only that state.
This is best understood with an example. Say there are 4 balls.
So what does this have to do with heat? So you can get my point. These colored balls don't have a damn thing to do with heat and how heat spreads in the universe, okay? It just doesn't have anything. It doesn't make any difference at all.
Balls to be distributed amongst 2 boxes. We could have all 4 in one, 3 in one, and 1 in the other, 2 and 2, 1 and 3, or all 4 in the second box.
It just amazes me that these people think the first half of this video has something to do with this nonsense. That somehow heat is confusing, because the little photons or something all mix up, and somehow because the photons mixed up, we don't know what the total energy is, or some kind of crap like that. It's just silly.
If these balls are all different colors, some distributions will contain a number of different microstates.
I mean, it really wouldn't matter, right? You're trying to do something. You're pushing a cylinder or something, and you have clumps of temperature, 70 degrees, 90 degrees, 400 degrees, 600 degrees. You know that the product is just going to be all of that stuff averaged. And that's what's going to push the cylinder. So who cares? How would any of this create a crisis in the universe? It wouldn't, in terms of understanding it as energy. Energy just doesn't come in this colored crap. And it doesn't matter even if it did come in this colored crap. It wouldn't make any difference, because all you're going to care about is what's its MV in the end. How much mass and how much velocity.
Statistical mechanics tells us that the most probable distribution will be the one with the most microstates. As in this case, the probability of...
So, we know in energy you can't create or destroy, so there has to be the same number of little crappers. So what's the difference? It's always going to be the same answer. 4, 4, 4, 4, 4. The energy is 4. Done. So it's just ridiculous.
Finding the system in one of these microstates with 2 and 2 is 6 out of the 16 total possible microstates. So this is a mathematical reasoning for why entropy tends to increase spontaneously in a closed...
So it's just so silly. So again, more words like spontaneously. It doesn't happen spontaneously. It isn't a random process. It isn't any of that crap. There's real causes and real reasons why this happens more often. It's not non-reasons. It's not magic. I mean, it's just terrible. This is such a terrible explanation.
System, whether this involves the dispersal of matter through space or the dispersal of heat energy from hot to cold objects. Entropy is an extremely difficult concept to grasp.
So it really isn't. Compression, expansion, compression, expansion. Not complicated at all.
And one could design an entire course around this subject alone.
And just imagine the failure here. I mean, the absolute truth is ask these physicists, why is the Earth molten? And there's only one good answer. Gravity. Well, if gravity is creating a huge amount of energy, how does that energy get into something called a bent space? Where's your evidence that energy in the vacuum creates bent space? It's obvious that the energy is creating gravity. The photons are doing it.
So don't worry too much if this seems confusing. For now, if we can just grasp a few basics about how the second law of thermodynamics was derived, we should be just fine.
So there was nothing in here that explained any way of deriving anything. And again, their argument is that somehow everything is increasing in entropy when there's just no evidence the universe is doing any of this stuff they claim it to be doing, where somehow it's radically changing over time, because the deeper they look, they find a lot of the same structure. And the structures would change if they're moving away from each other and all this bullshit was happening. If everything was getting colder, there'd be some evidence of the cooling process.
Let's check comprehension.
Waste of time, waste of time.
Thanks for watching, guys. Subscribe to my channel for more tutorials.
Yeah, don't do any of that. Too bad I don't have an audience to manipulate and control. But gee, it's just so bad that these people get supported in doing this lip service to real science. They just say stuff that's completely undemonstrated by anything called evidence, and they just claim it's true. It's just a religion, and it's being subsidized as if it's a science. And it's just really, really disappointing that that doesn't bother enough of you. Just doesn't. And I can't see that as anything other than, holy shit, human beings are scum. I mean, if they won't come to the rescue of science, little science is, and they won't come to its rescue and save it from being raped by religion. Yeah, you suck. So anyway, till the next time and such, and so forth and whatnot.